Welcome to another Explainer. Today, we're diving into the truly fascinating way math organizes itself. And to build a sturdy bridge to calculus, the source material suggests a pretty fun approach. We're going to pretend we're 4 years old again, just learning how to sort our toys. So, let's explore how visualizing simple boxes of toys actually lays the essential, rigorous groundwork for some of the highest levels of math. So you might be wondering, here's the big question for today's Explainer. Can simply putting toys into boxes really teach us the secrets of calculus? Well, according to the math, the answer is a resounding yes. You see, calculus is all about knowing exactly what numbers are allowed to exist and where they live. Before we can even touch advanced math, we need to know how to organize our numbers. So let's take a deep breath, tap into our inner child, and get to sorting. All right, let's kick things off with Section 1, Boxes of Math Toys. Okay, so a set is simply a box of things that belong together. Just think of it as a toy basket. The things inside the box, we call those elements. And those curly brackets you always see in math, think of those as the physical walls of our toy box. We give the box a big capital letter, like A, B, or C, and we put our elements inside. Let's look at 3 quick examples. Example 1, set A is a box holding the numbers 1, 2, and 3. Example 2, set B holds a cat, a dog, and a fish. And example 3, set C is a box exclusively for even numbers, like 2, 4, 6, and 8. If the number 2 is in the box, we say 2 belongs to A. Now, this isn't just child's play. Calculus uses this exact notation to know precisely what numbers are allowed to be played with in any given function. Now, what happens if we have boxes inside of boxes? We call that a subset. If every single toy in a small box is also found inside a larger box, that small box is a subset. Look at these first 3 examples. The box with 1 and 2 is completely inside the bigger box of 1, 2, 3, and 4. The letters A, B, C are entirely inside the bigger alphabet box. And our even numbers 2, 4, 6, they fit perfectly inside a box of numbers 1 through 6. But wait, what if the boxes have the exact same toys? We call those equal sets. And this illustrates a really interesting rule. The order simply does not matter. Dumping the toys in differently doesn't change the box itself. 1, 2, 3 is exactly the same as 3, 2, 1. ABC is the same as CAB. 2, 4, 6 is identical to 6, 4, 2. Calculus uses this concept constantly to compare different domains to see if they are actually the exact same thing. Sometimes, though, we have way too many toys to list. I mean, if I ask you to put all the odd numbers in a box, you'd literally be writing forever. So we use something called set builder notation. Think of this as writing a rule on the outside of the toy box. We use a vertical line that translates to such that. Let's walk through 3 examples. Example 1 gives us the rule for even numbers, 2 times n, such that n is an integer. Example 2 is a box for any number x, such that x is greater than 3. And example 3 is for any number x, such that x is less than 10. You just read the rule, and you instantly know what toys are allowed inside. Calculus relies heavily on this set builder notation to define complex domains for functions. Moving right along to Section 2, Mixing and Matching Boxes. Visually, there are 2 main ways we combine our sets. The union, which is symbolized by a big U, means dumping both boxes together into one giant pile. It means or. The intersection, on the other hand, symbolized by an upside-down U, is when we are being super picky. We only want the specific toys that are in both boxes. It means and. Let's look at 3 concrete examples for union. First, combining box 1, 2, 3 with box 3, 4, 5 gives us a new box 1, 2, 3, 4, 5. Notice we only wrote the 3 once. You don't count the same toy twice. Second, letters A, B unioned with C, D gives us A, B, C, D. Third, an apple and banana unioned with an orange and apple gives an apple, a banana, and an orange. Now, let's do 3 examples for intersection, finding what they share. First, box 1, 2, 3 and box 2, 3, 4 only share the 2 and the 3. Second, an apple, banana, orange box intersected with a banana, orange, grape box leaves us with just the banana and the orange. And third, what if we intersect 1, 2, 3 with 4, 5, 6? Well, they share absolutely nothing, which leads us perfectly to our next concept. When 2 boxes share nothing, or a box simply has nothing inside it to begin with, we call it the empty set, marked with a circle with a slash through it. It's literally an empty toy box. We can map all of this out visually using Venn diagrams, those overlapping bubbles you've probably seen a million times before. The overlap in the very middle gives us an instant picture of the intersection, and both whole bubbles combined represent the union. In calculus, when a limit simply doesn't exist, the empty set is the perfect mathematical way to explain it. Here are 3 great examples of the empty set in action. First, intersecting 1, 2, and 3, 4, 4, leaves us with nothing. Second, trying to find a number that is simultaneously greater than 5 and less than 2, totally impossible. Empty set. Third, intersecting A, B, and C, D, gives us an empty box. Now, when 2 sets create an empty set exactly like this, we call them disjoint sets. Imagine 2 kids playing with completely different toys. Example 1, 1, 2, and 3, 4. No overlap. Example 2, a box of cats and a box of dogs. No common elements. Example 3, even numbers like 2, 4, 6, and odd numbers like 1, 3, 5. They are totally disjoint. This logic right here is exactly how calculus handles mutually exclusive scenarios. Okay, let's jump into section 3, the number line pieces. I absolutely love this quote from our source material, from boxes of separate toys to pieces of the infinite number line. This marks a huge shift. Instead of just picking up individual, discrete block numbers, we're now going to take a virtual highlighter and highlight a whole, continuous piece of the number line. We call this highlighted piece an interval. So, the absolutely crucial point here is knowing exactly where our highlighted line starts and stops, and here's the kicker, whether we actually include those starting and stopping numbers. We have open intervals using round parentheses. This means start at A, stop at B, but do not include the endpoints themselves. Then we have closed intervals using square brackets. This means we do include the endpoints. Open intervals define open domains for calculus continuity, so getting this visual intuition locked in is key. Let's rattle off 3 examples for both to see how this actually works. For open intervals with our round brackets, example 1, 1 to 4 means everything between 1 and 4 but not the numbers 1 and 4 themselves. Example 2, -2 to 3 is strictly between -2 and 3. Example 3, 0 to 10 is strictly between 0 and 10. Now contrast that with closed intervals using our square brackets. Example 1, 1 to 4 with square brackets means 1, 4, and everything between them. Example 2 includes -2 and 3. Example 3 includes 0 and 10. The easy way to remember it, round means don't take it, square means take it. But what if we want to include one endpoint but not the other? Well, we call this a half-open interval, and we just mix and match our brackets. A square bracket on the left and a round on the right means we include the start but not the finish. This is an absolute game changer for understanding split or piecewise functions in calculus, where a line segment starts solidly but ends right before the next jump. Let's walk through 3 examples from our source material to ensure we've completely grasped this mixed notation. Example 1, a square bracket on the 1 and a round parentheses on the 5. This means 1 is included but 5 isn't. Example 2, a round parentheses on the 1 and square on the 5. Here the 1 isn't included but the 5 is. And for example 3, actually, scratch that. The source throws in a fun trick here. Square bracket on -3 and a square bracket on 2. This is actually a closed interval, where both are included. Just a great little reminder to always double-check the shape of your brackets. Section 4, Infinity and Finding Solutions. We call the endless direction infinity, marked by that famous sideways figure 8. And the source material points out something incredibly important here. Infinity is not an ordinary number. You cannot physically hold it like a toy block. You can't just treat it like the number 5 and do regular addition with it. Conceptually, it's a road that simply never stops. This idea of a road that keeps going forever is the foundational idea for all limits in calculus. So how in the world do we write an interval that never stops? Well, we use our infinity symbol with our brackets. Here are 3 examples. Example 1, round bracket 3 to infinity. This means all numbers greater than 3. And remember, since infinity isn't a number you can actually reach or include, it always gets a round open parentheses. Example 2, square bracket 3 to infinity. This means x is greater than or equal to 3. Notice the 3 is included with the square bracket, but infinity is still round. Example 3, -infinity to 5, both round. This means everything to the left of 5 going negative forever. We successfully capture forever just by using our box bracket notation. Pretty cool, right? Now we tie it all together to find solution sets. A solution set is just the specific toys that win the game by making an equation true. Look at these 3 examples. Example 1, what makes x plus 1 equals 4 true? Only the number 3.
so our solution set is exactly 3 inside curly set brackets. Example 2. What about x is greater than 5? Well, there are infinitely many answers, so we use an interval, 5 to infinity with round brackets. Example 3. What about 2 is less than or equal to x, which is less than 5? We write that perfectly as the half-open interval, square bracket 2, comma 5 with a round bracket. Finding these sets is exactly what you do when finding critical points when taking derivatives in calculus.
And finally, Section 5, the secret of calculus. This brings us to the whole shebang, the secret reason why math books teach sets before calculus. Calculus constantly asks one main question: which numbers are allowed? When you study domains, you're just defining the set of allowed numbers. When you study limits, you're looking at an interval of numbers, getting incredibly close to a target. When you take a derivative, you're talking about numbers in a microscopic interval around x. And when you do integration, you are literally dividing a closed interval into many tiny pieces. So the crucial takeaway is this: sets tell us what numbers we have, intervals tell us where those numbers live. Together, they build the entire house of calculus.
We started off today sorting toys like 4-year-olds. We put blocks in boxes, we checked if the boxes overlapped, and we highlighted stretches of the number line. Now, you hold the keys to the kingdom of advanced mathematics. You know exactly how numbers are grouped, bounded, and extended forever. So I leave you with this. Knowing what you know now about the fundamental building blocks of math, are you ready to step out of the toy room and into the infinite? Thank you so much for watching this explainer, and as always, keep learning.